Before a part is even manufactured, engineers need to know one thing: will it actually work? This is exactly where simulation comes in. Using tools like SolidWorks Simulation, we can predict how a design behaves under real-world conditions and identify potential issues before anything is built. In this video, we'll start by analyzing an air conditioner bracket as a single component, then as a multi-component assembly. So let's get started. So this is our model. This is the panel, this is the wall, and these two are the brackets. We want to analyze them. Simulation usually takes a lot of time when the model is complicated, and we need to make it as simple as possible. Sometimes we use 2D simplification and we don't even need to go into 3D. So let's simplify our model. For example, first of all, I can ignore the panel itself. Instead, I can apply its weights on the brackets. Next, we know that these brackets carry the same weight, which means that we can ignore one of them and apply the half of the weight on the other one. And the wall size is too much to discretize, calculate, and analyze it, so I need to decrease the size of the wall. And finally, our model comes down to this. As I told you, we run two simulations. The first one is the bracket itself, and the second one is the bracket that is connected to the wall by bolts. Now, from the SolidWorks add-ins, hit SolidWorks Simulation. The Simulation tab appears, go to it and click on New Study. And here you can rename the name if you want and confirm it. Here you can see that our design tree is split into two parts. And down here we have an extra tab, Static 1. If you want to go back to the model, you can go to this tab. Now, before running the simulation, it's important to understand the basic idea behind it. Most engineering simulations are based on the finite element methods. In simple terms, FEM works by dividing a complex geometry into many small elements, and these elements can have different shapes and different sizes from one model to another depending on the geometry and the level of the accuracy required. The behavior of each element is calculated individually and then combined to approximate how the entire model responds under loads and constraints. These calculations are typically solved numerically using iterative methods, allowing us to handle complex problems that are difficult to solve analytically. So I don't want to go into details, I just wanted you to have an overall insight of what's going on in SolidWorks Simulation. First thing we need to do is to define the project. We need to define the element type, the connections, fixtures, boundary condition, external loads, and finally create the mesh. The order that we define the parameters is exactly the same here, from the top to the bottom. So let's start with the part. Here we can do three things. First of all, we can exclude any part we don't want them to be involved in the simulation. Since we want to start the simulation with a single component, I want to exclude the wall from the simulation, and for this right click on it and hit exclude from the analysis. The second thing you can do here is to specify the material if you want to try the simulation with different materials to decide which one is best for our model. Now right click on it and apply edit material, and alloy steel is okay, apply and confirm it. And the third thing we can do is to assign the element type. We have three element types: truss, beam, and solid. And since we combine our three elements into one solid body, I would right click on it and hit treat as solid. The next item is the connections. Here we can define the connections between different parts or faces. We can define pin, bolts, global interaction, or local interaction if you want to apply friction. Since we want to start with a single component, we don't have any connection here, so I would delete anything that I see here. Next, in the fixture, we can define the boundary conditions and right click on it and go to fix geometry. And I want the back face to be fixed. I click on it, which means it is not allowed to move in X, Y, Z directions, and confirm it. Now it's time for the external loads, and here we can apply force, torque, pressure, gravity, etc. Let's start with the force. So if you remember, the panel was set on this area, but if I select this face, it grabs it all. But if you remember, the panel started somewhere around here. There was no direct loads on, for example, the first 50 millimeters of the face. So in this situation, I need to split the face. For this, I need to right click on the bracket and hit edit part. Then I'm gonna go to this face sketch mode. Now I wanna create a rectangle, and the distance between this edge and this edge is 50 millimeters. Confirm. Exit the sketch. For splitting, we have a very special tool called the split line. Now from the menu, go to Insert, and from the curve, select a split line. The first block is the sketch, and the second one is the face. And then I'm going to confirm it. Now, as you can see here, I have two separate faces. Now, exit the editing mode, and let's go again to external load force. And I'm going to select this face, and the unit is SI, and the amount of the force is 500 newtons. Confirm it. The next step is meshing. Meshing is the process of dividing the model into many small elements, and these elements are where the solver actually calculates the physical behavior of the part. So right click on the mesh and let's go to create mesh. And here I have a slider which I can adjust the mesh density. A finer mesh improves the accuracy, especially in critical regions, while a coarser mesh saves some computational times. The key is to refine the mesh where it matters most. In this case, I usually start with a standard mesh with the default values and then refine it where necessary. So I'm going to reset the parameters to the default values and then I'm going to confirm it. Just remember that the default values are a good starting point, not the final solution. So let's confirm it. Well, obviously the quality of the mesh is not sufficient for accurate results. The mesh is too coarse at some regions, and so many elements are not well shaped. It is not very good for accurate stress predictions. So we need to refine it. Now let's go and recreate the mesh, but this time I'm gonna change the parameters. So activate mesh parameters. Make sure that it is set unblended curvature based mesh. It gives more flexibility. And then I'm gonna decrease the maximum element size, for example, to something like, let's say, 8 millimeters. And I want it to be a little bit more uniform, so I increase the minimum element size to something like maybe 6 millimeters. I decrease the element size growth ratio to 1.2, and then I'm going to confirm it. This one is actually much better. Even though that we have some anomalies, for example, we still have some stretching or maybe some distortions, for example, around the holes. But in overall, it's good enough for us to proceed. Just so you know, in more specialized softwares like ABACUS or ANSYS, we have very special tools for creating the mesh, and one of them is partitioning, which is the process of dividing the model into smaller regions to have more control how to create the mesh in each region. I don't want to go any deeper, so let's go and right-click on a static one and hit run to run the simulation. Now here we have the stress analysis one mices we are talking about. And this one is the exaggerated plot of the simulation. If you want to make it more realistic, you need to right-click on it and go to chart options and switch to definitions. And here deform shape, change it from automatic, which is 400 times, to user defined, and let's make it, for example, 150 times, and then confirm it. And from here, I can decrease the maximum amount of the von Mises. Right now, it is 50 megapascal. So let's make it 12 megapascal, 12E plus 6. Now, obviously, we have a critical region on this area where two profiles are attached, which makes sense because from the equilibrium equations, we have higher reaction forces. But what if I want to see the amount of the stress in different spots? For this, right-click on the stress and hit prob. And if I click on different spots, I can see the amount of the stress here. For example, this one is 6 megapascal. Here we have almost 12 megapascal. Down here we have something like 40 megapascal. And maybe here it is 50,000 pascals, and just like that. So I'm going to confirm it. But we need the critical point too, the point with the highest amount of the stress. And for this, right-click on results and hit list stress displacement strain. And select your field variable, set the type, and then confirm it. The highest amount of stress happens in this location, and its amount is almost 50 megapascal. If you want to see the other analysis, for example, displacement, you just need to double-click on it. And the maximum amount of the displacement happens at the tip of the bracket, and its amount is 0.12 millimeters. Just out of curiosity, let's change the external load from 500 to 5000 and see how things changed. So I need to run the simulation once more. Now let's fix the scale and go to the chart options from the definition. This time I'm going to make it maybe, for example, 20 times bigger. I'm gonna confirm it. And here again, I'm gonna change it to, for example, 80 megapascal, or maybe I'm gonna make it 100 megapascal. Now, as you can see, the critical regions this time is much higher, and the yield strength is almost 600 megapascal. So let's go and see what is the critical point. So I'm gonna confirm. And here the highest stress is something like 500 megapascal. It is 10 times bigger than the previous one, which means our safety factor is much smaller this time and we need to be more careful about it. But how things are different when we have an assembly. So what I want to do here is to bring back the wall into the analysis, right click on it and include in analysis. And we need to walk through the parameters once more. So here in the parts, I need to assign the material for the wall. So I'm going to right click on it and apply it. And here I don't have a building material for the concrete. So what I want to do is to go to custom materials, and from the beam truss, the last one I changed the name to from user defined 3 to concrete. And here are the values that I applied here. So apply and close it. Another assumption is that the wall is rigid, so I'm gonna right click on it and hit make rigid as well. Moving on, we have connections this time, and the connection type is bolt between the bracket and the wall, so I'm gonna right click on it and select bolt. I'm gonna switch it to counter bore screw, and for the edge I need to select, just make sure it is the outer edge, and we need to select the thread surface as well. You can apply a little bit of preload, for example 5 Newton meters, and then confirm it. Do the same for the next 3 connections as well. And finally the connections would be like this. Also, we need to apply another connection here as well, the local interaction. And for this I need exploded view. So I'm gonna switch to configurations, and let me bring it down. And I'm gonna hit explode, which by the way, you know how to do this from my assembly tutorial, right? Okay. Now let's go to the connections, and I'm gonna create another connection, local interaction, select this face and this one. By local interaction, I'm telling SolidWorks that these two faces are not allowed to pass each other. And down here, you can define the coefficient of friction if you want. And finally, you can confirm it. And the next one is the fixtures. So I'm going to edit the fixed one. But instead of the face of the bracket, this time I'm going to select the face of the wall. And then I'm going to confirm it. Bring back the external load to 500. So I'm going to collapse it. And finally, it's time to recreate the mesh once more. So I'm going to right click on it and hit create mesh. I want to create the mesh with the last parameters from the previous simulation. So let's select it and confirm it. And as you can see, the mesh creation fails. It happens a lot, and the first thing you need to do in situations like this is to decrease the mesh size. So let's go and click create mesh once more. And this time I'm gonna change the maximum element size to 6 and the minimum element size to, for example, 3. And let's run it once more. We nailed it. Its quality is good enough for us, but if you want to see the mesh quality in the common face, you need to take exploded views again. Right click and hit explode. Maybe I need to switch to model and come back again, and let's show the mesh. Now here we have acceptable quality. Though still we have a little bit of distortion around the holes, but it's okay in overall. Another trick here is that, as you know, our main focus of the analysis is on the bracket, and a finer mesh is more accurate and a coarser mesh saves some time. So I can apply a fine mesh on the bracket and a coarse mesh on the wall. And for this, we can use a very special tool, which is mesh control. Right click on the mesh and hit apply mesh control. So here I'm gonna select the wall. We need to recreate the mesh once more, so let's go and confirm it. As you can see, we have a coarser mesh on the wall and a finer mesh on the bracket, and which is an optimized method, and we don't need anything else. Let's run the simulation once more. This one takes much longer. Okay, here we go. As you can see, the color of the wall is different, which means it doesn't take any stresses. So for example, if I select prob, for graphical issues, the wall is actually here. So select different spots, the value is 0, 0, 0, 0. So what I can do here is to hide the wall for better visualization of the plot. And I'm gonna hide the wall. Go back to the static and double click on stress. And decrease the highest 1 MySys stress to something like 30 megapascal, 12 megapascal. Let's make it. So again, we have critical regions in this area, and of course we have some other critical regions on the back side around the holes as well. This is considerable. Let me hide the connections. As you can see, there is a high amount of stresses on the back side which wasn't visible in the previous simulation. So while simplification is necessary, we need to be more careful about it. And the wall itself, even though it wasn't included in the analysis directly, but its existence was necessary for the results. Okay guys, let me know if you have any questions. Just remember that the accuracy of the results heavily depends on how well you define the model, especially the mesh. Simulation is all about understanding the process behind and using it to predict real-world behavior so you can make better engineering decisions. If you found this helpful and you want to see more, make sure to subscribe to the channel. And as always, from one engineer to another, see you in the next one.